All right, it looks like we have folks logging in right now, but since we have a healthy subset of those who have registered, we're going to get started as there's a few administrative items and acknowledgements that we'd like to work through, and then we have a lot of information to get through today. So welcome and thank you for joining us from wherever you're joining us here today. Presumably most of you are from across Canada, but we do know we have some participants overseas as well. My name is Josipa Petrinic. I'm the president and CEO of CUTRIC. We have here today my colleagues Mohammed Karouf, who will be walking us through some of the deeper analysis that fed into the Saskatoon decarbonization planning work that we had the privilege and the honor of doing with the City of Saskatoon and Saskatoon Transit. I have also on the line our colleague Bernard Ross, who is another one of our technical leads and analysts who also worked on the project with us. And of course, we have our colleague Mike Mullenrek from Saskatoon Transit as well joining today. So with that, we're going to get started. And first and foremost, we'll move through to the material. Now, this is a public webinar, but we always do indicate that there may be confidential information in here. We do ask that you don't take this deck and present it yourself without reviewing with us. We have removed most of the non-disclosure, well, in fact, all of the elements that are protected by non-disclosure agreements. But again, we do ask, just because the nature of the material, that if you are going to present it in any public forum, that you do get our approval to do so first, so that we can make sure all the project partners in the project approve of the dissemination and use mechanism of the materials. So we will move forward to the land acknowledgement. And I do want to acknowledge that CUTRIC staff is based across Canada. And I am joining you here today from the Niagara region and from Toronto, specifically on the way to the Niagara region. So I will acknowledge that CUTRIC takes actions beyond the land acknowledgement itself as part of our reconciliation efforts. We do have a gender and racial diversity policy in place that encourages the hiring of diverse voices. We are a woman-led organization right now at the board of directors, and we have been 60% or more female-led since 2018, and we're extremely proud of that. We're the only technology innovation corporation and firm in Canada to hit those standards. We do support Indigenous-led businesses as well, when possible, with contracts to support economic growth within and among our Indigenous communities in Canada. And we support research and federal investment into the exploration, investigation, and analysis of missing and murdered Indigenous women and children, and the mass and unmarked graves of children that went missing as part of the residential school system in Canada. So we are firm believers as a research and development technology consortium ourselves within the nonprofit sector that federal funds need to be going into the search for those missing and murdered individuals and for the children from Canada's historical residential school system. We ourselves strive to make Canada a greener place and support climate change initiatives, including through innovation that does support better mobility in Canada. And I'd like to acknowledge here today that the land where I am joining you from, between Toronto and Niagara, is land on which we gather and recognize as the traditional territories of many nations, including the Mississaugas of the Credit, the Anishinaabe, the Chippewa, the Haudenosaunee, and the Wendat peoples. Toronto is covered by Treaty 13, and it is with the Mississaugas of the Credit. We acknowledge the deep and lasting relationship that these nations have had with this land, and we recognize that they have been the custodians of this land and water for millennia. We do respect those generations of Indigenous peoples who have cared for the territory, continue to do so today, and who allow us to take the opportunity to join and live on this land together in peace and prosperity. We recognize our responsibilities as treaty partners and commit to moving forward in the spirit of reconciliation, respect, and collaboration with all Indigenous communities to the extent that we can do so, and in good faith. So thank you very much once again for joining us from across the country and beyond. We will now move to the agenda to walk folks through here what our intention is here today. As the context is that we completed this fairly extensive project with Saskatchewan's Saskatoon Transit. It is one of more than 30 studies we have done and standardized across the country with the federal government Zero-Emissions Transit Fund, as CUTRIC is the preferred nonprofit provider of zero-emissions transit feasibility and planning services for transit agencies. And that includes both predictive planning, which is what we're going to go through here today, and post-deployment empirical analysis to see how are the vehicle systems operating vis-a-vis what was promised from manufacturers as part of the predictive studies. Very often we merge where there's empirical evidence, we merge it into the predictive study, and there's quite a bit of that embedded into this study here today. And we do know that some of the results may have been concerning to members of the public. In Saskatoon and beyond, we ourselves consider ourselves an environmental organization. We're certainly dedicated to the decarbonization of Canada's transportation system. So we do believe that through education and public dissemination of results and inputs, that we are able to help create common ground where we can actually create the best evidence-based solutions for Canadian transit and public mobility. We're going to walk through the introduction of the project, move to an overview, spend the bulk of the time today into modeling results, look at the environmental life cycle assessment, some of the assumptions that went into it, the full fleet decarbonization plan with facilities assessment. There is a social analysis that we do in all of our studies, which is increasingly important as the federal government now also requires transit agencies to have a housing density analysis. So we will walk you through the income analysis and the other social metrics that we take a look at. And then the economic analysis of decarbonization, along with the decision-making matrix that does allow folks to understand cost is not the only driving factor. Of course, it's cost, emissions, and complexity variables that drive an agency towards a decision about how they will decarbonize or plan for decarbonization in upcoming years. We'll turn to the conclusions of the study, and then we're going to spend some time on an FAQ. What we were able to do is look at council minutes and hear out the voices of the environmental groups and others that presented at Saskatoon City Council meeting, which we were part of. There were several concerns raised, questions, criticisms. We've taken those, and we are going to respond to the top ones that appeared repetitively, either in council or in online fora. And then we do invite folks to pose their questions in the chat function, and we should have enough time to address a couple of them. We will be posting the FAQ online on a landing page associated with this project, and any questions we don't get to today, we will incorporate into that FAQ. So with that, we'll move forward to our introductions and start on the technical material. I first want to thank Housing, Infrastructure and Communities Canada, formerly Infrastructure Canada. They do run the Zero Emissions Transit Fund federally, and now the Canada Public Transit Fund, which we are strong advocates for. And I come to hot off a round of meetings in Ottawa yesterday across the ministries that are touching on that funding program for transit, including the funds within that support zero emissions decarbonization capital procurements. Of course, the team at CUTRIC is the team that has done the technical work in partnership with Saskatoon Transit and Saskatoon Transit that has been part of the project hand in hand. And that is exactly the kind of collaborative relationship that produces the best, most detailed evidence-based outcomes for transit agencies that are in the flux and in the transition pathway for the next decades. I'd like to introduce here our colleague, Mike Mullenbeck from Saskatoon Transit, who will introduce not only himself, but also Saskatoon's role in the project. Welcome, Mike.
Thanks, Josipa. And good morning, everyone, and welcome to today's webinar on Saskatoon Transit Zero-Emission Bus Feasibility Study, delivered in partnership with our friends here at CUTRIC. My name is Mike Mullenbeck, and I'm the Director of Saskatoon Transit, and I'd like to begin by thanking you for joining us as we share the outcomes of a project that represents a step forward in our city's commitment to sustainable transportation. This webinar is part of a broader national effort under the Zero-Emission Transit Fund, which supports municipalities across Canada in transition to cleaner, more efficient transit systems. For Saskatoon, this means exploring how we can move forward toward a zero-emission bus fleet in a way that's both operationally viable and financially feasible. Saskatoon Transit engaged CUTRIC to conduct a full fleet emissions bus implementation plan, and this study was staged in 5 different phases and assessed the economic, technological, social, and environmental dimensions of transitioning our diesel bus fleet to battery electric and hydrogen fuel cell buses. CUTRIC performed a detailed state of readiness assessment of our fleet and facilities, followed by advanced modeling to evaluate energy consumption, route feasibility, and operational constraints. 3 battery electric bus models and 1 hydrogen fuel cell bus configuration were analyzed, and the study explored whether a 1-to-1 replacement of diesel buses with ZEBs was feasible, considering depot and on-route charging infrastructure. While the findings confirm that the full fleet conversion is not financially feasible in the short or medium term, the study provides critical insights to guide incremental planning. It also highlights the importance of monitoring the advancements in technological funding programs and the decarbonization of Saskatchewan's electrical grid to make future electrification more viable. So today's session will walk you through these findings in more detail, and with that, I'll pass things back to the CUTRIC team to provide a closer look at the study's findings.
Thank you so much, Mike. And I think that's the critical element, is creating the outcomes that help folks plan more efficient, optimized transit communities in the future. And certainly decarbonization is not the only goal, but it is a primary goal of public transit in Canada today. So we were excited to be part of that. Now let's turn into the introduction overview of the methodology, and then I'll turn to my colleague Mohammed Karouf, who will walk you through the modeling results and into some of the technical outcomes. So just first off, we know that one of the concerns and criticisms that we heard certainly at City Council and elsewhere was there's no methodology, that these are numbers on a page. I'm very happy to report there's a lot of methodology that goes into these work products, and they've been developed well over half a decade ago, and they've been refined through multiple rounds. So we're now into our RUDI 3.0 generation tool set. These tools are reviewed, analyzed, assessed, criticized, reviewed again, and innovated with our transit partners project by project over multiple iterations. And like any good software tool or algorithmic tool, you go through multiple versions as you learn more and more. And now, since there's empirical evidence coming out of the industry, we have started to modify some of the assumptions in the tool set to balance empirical performance with manufacturer specifications. So just to walk folks through how a project typically starts is a typical project scoping. The scope of work is standardized with the federal government from A to Z, all the things you have to go through in order to be able to qualify for capital funding. And Mohammed will be walking you through the main elements of those. It's not just the physics modeling, it's the facility assessment, it's the life cycle assessment from well to wheel, from cradle to grave rather, of the life cycle emissions of the products. It goes into the data collection period then with the transit agency, obtaining the data that they do have. Not all transit agencies are equivalent in Canada. Some have really, really refined data about their blocks, their routes, their vehicles with telemetry. Some do not, in which case we have to do meta-level build-outs and digital twinning of the city to be able to model it out. There's a detailed GIS analysis, and so what we look at is not average blocks or average routes or average distances. We look at every single block, every start-stop, every stop sign, every yield sign, every pedestrian crossing, every intersection that results in a slowdown, a stop, or an acceleration, because it consumes energy. We have multiple duty cycles, so we look from light duty to heavy duty and the medium duty cycle in between, with winter and summer conditions integrated. That walks us into the energy modeling optimization. Apropos of what Mike just mentioned, multiple vehicles are then modeled in there. There is not an infinite number of transit vehicles available in the electrified domain. You can count the number of makes and models available in Canada on your hands, and so it is possible to model multiple of them and capture the bulk of the potential industry that you would buy from. Then we look at the facilities, because almost never will you get a one-to-one bus replacement with diesel. So then you have to look at whether the facilities can handle the power load required, whether extra facility space is needed, what that means in terms of facility build out and cost. And then we look at from start to finish, based on where the city wants to get to from an emissions reduction standpoint, how many vehicles have to be procured at what timing, how many chargers, how many kilograms of hydrogen, at what time, what year, in order to hit that target. And then we calculate out the economic cost of doing that, along with the social and environmental costs or benefits. And then we look at the implementation plan, which is the year by year. This is what you need to do starting today in order to hit your emissions target with the economic funds that you will need in order to achieve those goals. So that's the methodology. And if we move forward one slide, folks who do want to learn a little bit more about RUDI 3.0 and all of the CUTRIC nonprofit tools we've developed with our transit agencies and quality controlled for over the years, we'll drop a link to our website where we document that. In this project, like with most zero emissions transit fund projects, we look at scenario 1, which is a full battery electric bus solution, assuming you only use battery electric buses and assuming that you start first with just depot charging. How many vehicles will successfully deliver their blocks? How many will fail? And by failure, Mohammed will go through that and identify a failure as a state of charge drop under 20%, and the vehicle can't return to the depot with sufficient energy. And then we look at in-depot and en-route charging. En-route charging is very effective at elevating the rate of success of electrification, but it's also very expensive. Each charger is well over $1 million, and that's not including civil works. So these are price points to balance out with electrification extension. We look at scenario 2, which is if you ignore battery electric buses and you just look at hydrogen fuel cell technology, what can that do for you? And do you need refueling? Sometimes it is true that even hydrogen fuel cell buses do not achieve a one-to-one bus replacement with diesel. Sometimes they will need refueling as well, depending on the tank size. And then 3, we often find that the optimal solution is an optimized mix of battery electric and hydrogen fuel cell. And you can optimize for complexity, replacement ratio, cost, and emissions. And sometimes you find that the lowest cost and the best emissions profile is achieved by applying battery electric buses and hydrogen to the best applications within a route, and you achieve the best of both worlds. Not in all cases does it work, but in some cases it does work to be the best and optimal solution. So we'll go forward one more slide. Just methodologically on the back end, these are some of the high profile elements that go into the Route I 3.0 toolset. So when we take all of the vehicles, all of the blocks, all the makes and models, all the facilities that we need to address, we then take a look at those duty cycles. So we look at light, medium, heavy duty with seasonal variations on the HVAC system, and we use ridership scenarios from the city itself. Some cities do not have accurate ridership numbers. That is still a problem in Canada, especially smaller agencies. In those cases, we may use estimates of how full the bus can be. In some cases, the cities have absolutely accurate ridership numbers, but they're already bursting at the seams. So they know their buses are packed, and they ask us to look at exceptional ridership numbers. So we work in terms of generating the duty cycle. How much energy is the vehicle going to consume because of not only the seasonal variances and the HVAC, but also the ridership, the weight of the human bodies on that bus, combined with, on the right-hand side, the route profiles, the topography of the landscape, the hills, the inclines, the slowdowns, the stops, the speeds, and the traffic schedule and the transit schedule. So those things are integrated because the same bus performing on different routes under different conditions will perform extremely differently. So there's just simply no such thing as what's the average range of a bus. It is what is the range of the bus in those conditions under those loads on those routes. And that is the level of precision we engage in. And then we look at taking that through the vehicle makes and models that we pull from the manufacturers based on what they are selling in Canada. Sometimes we will do a Frankenstein vehicle. Sometimes a transit agency will ask us to patch together a vehicle that does not exist in the marketplace today. And we can work with manufacturers to put together a Frankenstein vehicle of a hypothetical, what would this kind of vehicle look with this load, with this battery pack, et cetera. But generally speaking, in order to obtain capital funding, you have to model real vehicles that you could really truly buy. And so we look at manufacturer specifications that are actually in the marketplace today. And as Mike noted, and Mohammed will review, there's multiple makes and models embedded into this project. And then ultimately, we look at the charging schedule and the fueling schedule along with that for both battery electric and hydrogen. So those are the core variables in the Route I 3.0 toolset, but there are dozens of more variables, many of which are NDA protected because they come right off of the manufacturer's specifications of the vehicle. So if we go forward one more slide. Here you will just see the summary component, which is we run all of that through 3 baseline duty cycles. These are just the baselines, and then additionals are added. So you've got the light duty cycle here, which is just the person on board with the driver. The average stop frequency of the stop starts, yield signs, traffic lights are assumed to have an average stop frequency of red light, green light, yellow light. Medium duty has an average bus passenger capacity on top of an average stop frequency with average auxiliary loads. So that will mean that the HVAC is turned on an average. Typically, it's 50% of the max load, but not always. Sometimes we will be able to get actual HVAC loads from the transit agency, and that determines the number of kilowatts in terms of the power that it's drawing and the kilowatt hours that it will consume in terms of energy. And then heavy duty is the worst case scenario, and we often encourage transit agencies to really look at the heavy duty as the worst, and then plan for medium to heavy duty in and around there in terms of what you buy, when you buy, and how you decarbonize. The heavy duty assumes maximum passenger load. Every stoplight is a red light. Every yield sign is a slow down, properly done. Every pedestrian crossing has a pedestrian walker across it. And we assume maximum auxiliary load. So HVAC is turned on, either heating is going full blast or air conditioning is going full blast. And then we look at running those buses across the blocks actually in Saskatoon, and then determining how do the BEBs perform and how do the fuel cell buses perform at any point in their daily service with those loads. Do their state of charge on their battery pack drop below 20%, which is typically the cutoff manufacturers will allow for before the warranty is void and null. And so 20% is the state of health for the battery for longevity, but also a warranty condition. Same thing with fuel cell buses. As Mohammed will explain, fuel cell buses in Canada are designed to be battery electric buses with a fuel cell converter on board with hydrogen on board as the range extension mechanism. So ultimately, those batteries also have a state of charge level, but typically we will see failure when the tank runs out of hydrogen, and that is how we define a failure on a fuel cell bus. So now we'll move into the modeling results. And the modeling results, we will turn to my colleague Mohammed Karouf, who will now walk you through over the next approximate 25 minutes into some of the detailed outcomes, and then we'll move into the FAQ. Over to you, Mohammed.
Thanks, Jasper and Mike. I'm Mohammed Karouf, a technical director at CUTRIC, leading decarbonization initiatives across Canada from coast to coast. It's an honor to contribute to the transformative efforts underway in Saskatoon. Thank you all for joining. Now let's dive into the results of this comprehensive modeling. This slide presents the average energy consumption rates we calculated for both battery electric buses and fuel cell electric buses. On the left, you can see the BEV consumption in kilowatt hours per kilometer. We modeled two battery sizes. As expected, the energy consumption rate increases significantly from light duty to heavy duty cycle, as Josipa was explaining, reflecting the higher energy demand of frequent stops and acceleration with the full passenger load. On the right, we have the FCEB consumption in kilogram of hydrogen per 100 kilometers. We see the exact same trend here. Consumption is lowest during light duty and highest during heavy duty across all service days. These figures are crucial for calculating ongoing operational costs and infrastructure requirements that we will be presenting in next slides. Here we see the operational success rates, which is the percentage of service blocks that could be completed with the battery dropping below a 20% threshold. The chart on the left shows the BEV success rates for the blocks using a strategy of both in-depot and on-route charging. While the BEV with a larger battery performs well in light medium-duty cycle, both models show a significant drop in success rates on the heavy-duty blocks, particularly on Saturdays and weekdays. This highlights key operational challenge for a BEV fleet, which we can mitigate with block splitting, as we will explain later as well. The fuel cell electric bus chart on the right, which assumes depot-only refueling, also shows high success in light medium, but struggles with heavy-duty blocks, with success rates dropping to around 60%. This tells us that regardless of the technology, serving the most demanding routes will require some careful operational planning. Next slide. Now, to address the challenges with BEV success rates, as we said, en-route charging became a necessity with Saskatoon. So even with en-route charging, we've seen that some blocks were not able to do it. So based on our analysis of routes, layovers, and energy deficits, we've identified 4 key locations for en-route chargers, in addition to the main depot of the Civic Operations Center. These proposed sites are the Confederations Terminal, the Lawson Terminal, the Market Mall Terminal, and the Center Mall Terminal. Placing chargers at these strategic layover points would allow buses to top up during the days, significantly improving their ability to complete demanding service blocks. And it adds also, of course, a lot of interface management that will be involved in these exercises in the design and construction phases. Next slide. Let's look at the environmental performance of each scenario from a life cycle perspective. Next slide. This chart shows the total global warming potential for each scenario over its entire life cycle. Before we analyze the results, it's crucial to understand what this chart actually represents. So this is a comprehensive cradle-to-grave life cycle analysis. This is a much broader scope than some other environmental analysis, which might focus only on emissions from electricity used on the to power the bus, for example. Our approach includes emissions from vehicle manufacturing, battery production, infrastructure construction, well-to-wheel fuel production, including the different energy pathways for creating hydrogen, even the energy needed for facility heating, cooling, and end-of-life cycle recycling as well. So now, looking at the chart, you can see the impact of this detailed approach. The base case is the current diesel fleet. Scenario 1, full BEV solution, shows a modest reduction in emissions, around 10-15%. Now, looking at scenario 2 and 3, where hydrogen buses are getting involved, the results are heavily dependent on the type of hydrogen used. So using hydrogen from wind power offers the most significant emission reduction. However, if hydrogen is produced using electricity from the current grid, what we call here a grid hydrogen, it results in a massive increase in emissions compared to diesel. This is a critical finding that the potential of hydrogen in buses is entirely tied to the carbon intensity of that hydrogen that you will be using, whether it's produced by SMR or through electrolysis from the grid or through electrolysis from a clean source like wind or solar. Next slide. So how would Saskatoon Transit transition their fleet under these scenarios? Let's look quickly at the proposed timeline in the next slide. We've mapped out a phased multi-year implementation plan for each scenario, running from 2027 to up to 2024. Up to 2041. For scenario 1, the transition would start with 66 BEVs in stage 1 and grow to a full fleet of 278 BEVs by stage 3. In scenario 3, it involves rolling out 70 fuel cell electric buses initially and ultimately 298. In scenario 3, the mixed fleet, we begin with 98 BEVs in stage 1, followed by the introduction of FCEBs in stages 2 and 3. Each plan is designed for a gradual, manageable transition over approximately 15 years. Next slide. Now, a transition of this scale requires significant changes, as we said, to transit facility. So let's review our high-level assessment, class 5 assessment that we did in the study. Next slide. This slide provides a high-level summary of the facility retrofit costs and infrastructure needed for each scenario. Scenario 1 was the most expensive in terms of facility retrofits, which with a total of $47.8 million. This is driven by the need for 93 charging cabinets and a significant electrical service upgrade of 5 megavolt amps. Scenario 2 requires around 18 million investment for hydrogen infrastructure, including 12 fuel dispensers and 20,000 kilograms of on-site storage. Scenario 3, the mixed fleet lands in the middle, around 27.7 million, requiring a combination of both charging and hydrogen infrastructure. Next slide. Here we have a more detailed breakdown of those facility costs. As you can see, for scenario 1, the costs are dominated by the charging infrastructure itself at 23.7 million, and the necessary electrical upgrades are nearly 12 million, which most likely live for longer, like for around 30-40 years, but charging infrastructure may live for less than that. For scenario 2 and 3, the main cost driver for hydrogen infrastructure, 13.6 million and 10.8 million respectively. All scenarios also include costs for commissioning and 30% contingency to account for unforeseen issues, as this is a class 5 estimate. The totals at the bottom align with the summary in the previous slide. Next slide. Beyond the technical and financial aspects, we also conducted a social analysis to understand the community impacts of fleet electrification. So our social analysis considered several factors to identify which communities could benefit most from a transition to zero-emission buses. We looked at areas with noise sensitivity, communities already exposed to high level of air pollution, and those with high concentration of vulnerable populations. The goal was to use fleet transition as a tool to advance social equity here. Next slide. By mapping those social factors against the transit network, we developed a priority score for each route. This table shows the highest priority routes for the deployment. Routes like Meadow Green, City Center, and City Center Confederation scored the highest due to a combination of high ridership, frequency, and service to areas would benefit most from reduced noise and air pollution. This provides a clear roadmap for socially conscious rollout. Next slide. Now let's turn to the comprehensive economic analysis. To ensure transparency, this slide outlines the key assumptions that underpin our economic model. We use a discount rate of 3.5%. You can see the assumed acquisition costs for each bus type. We have also detailed our assumption for annual parts, replacement, maintenance, and the average price of fuel and electricity, including the price of $25 per kilogram for the hydrogen. It's also worth noting that how different assumptions can impact a cost analysis. For example, some previous total cost of ownership reports have assumed an identical 18-year lifetime for both diesel and electric buses. Our model utilizes distinct inputs for each technology, which is OEM-driven data. These details are crucial for understanding the financial economic results, which are gonna be in the next slide. Here are the total economic outcomes for each scenario over a 15-year life cycle for the project life cycle. The diesel base case has a total cost of around $262 million. The scenario 1 totaled at $479 million. Scenario 2, the FCEB solution, was the most expensive with around $1.1 billion, driven by the high capital and operational costs, hydrogen costs, essentially, which was again assumed at $25, which is a bit modest number. Scenario 3, the mixed fleet, has a total cost of $588 million. As you can see, the zero-emission bus scenarios represent a significant increase in total cost. It's important to understand the scope of these numbers as they may differ from other analyses. Unlike some previous reports that may have focused almost exclusively on the vehicle itself, our economic analysis is comprehensive. It includes not only the vehicle, but also the significant upfront capital cost of the charging and fueling infrastructure, which we detailed in the facilities assessment. This provides a much more realistic picture of the total investments required. Given these complex trade-offs between cost, environmental impact, and operational feasibility, now how do we arrive at a recommendation? This brings us to the decision-making analysis that we did for this study. We used a multi-criteria decision-making analysis that balances 3 equally weighted objectives that will be shown in the next slide. Maximizing carbon emissions measured by the global warming potential we saw earlier. Maximizing ease of transition, which is measured through the vehicle replacement ratios, essentially how many zero-emission buses are needed to do the work of a diesel bus. And then maximizing the cost effectiveness, which is measured by the total project cost that we just reviewed. This framework ensures a balanced and holistic recommendation, not one or biased one, like based on a single metric. Next slide. This table shows the final outcome of that analysis. So we scored and ranked every scenario, including different hydrogen production pathways, against the criteria mentioned in the previous slide. After weighting and combining the scores, the result is quite clear. The base case achieves the highest final score, and it's ranked first. It scores exceptionally well on the cost effectiveness and ease of transition, of course, because you don't have to have a replacement ratio here, which outweighs the stronger performance of some zero-emission bus scenarios on emissions. Among the zero-emission bus options, the fuel cell electric bus solution using hydrogen from wind power ranks highest at number 2, primarily due to its very strong emissions score. The full BB solution lands at rank number 4, and that's mainly because of the relying on the grid for charging, and the Saskatchewan grid is yet to be cleaner, which is promised in the long term, but in the short term, these are the scores that are outlining the emission score for the battery electric buses. Next slide. Let's summarize the key findings from our study. This table provides a final side-by-side comparison over 15 years period, the diesel-based case has the lowest total life cycle cost. In contrast, the zero-emission bus scenarios are significantly more expensive. In terms of emissions reduction by 2048, the BEB solution offers a modest 10% reduction, while the FCEB and mixed fleet scenarios have a very wide range of outcomes, from 57% reduction in case of the wind-produced hydrogen to 100% increase in emissions, depending entirely on like the hydrogen score for the type of hydrogen used. The diesel to zero-emission bus replacement ratio shows that more zero-emission buses are needed to provide the same level of service as the current diesel fleet, of course, leading to a larger required fleet size by 2048 for all the scenarios. In this final section, we want to address some common critiques and frequently asked questions about this analysis. Next slide, please. One critique we've heard is that the report underestimates the benefits of electric buses by using pessimistic assumption about Saskatchewan's dirty power grid. Now, we see this as misleading, and our fact check shows that the analysis uses the current carbon intensity of Saskatchewan grid, which is high at around 500 grams of CO2 equivalent per kilowatt hour. This high intensity is the reason for the modest 10 to 15% reduction we saw earlier for a full BEB fleet in scenario 1. It's also important to note that using the same grid power for electrolysis to produce hydrogen in the same way, it actually increases the total emissions by around more than 100%. While a future cleaner grid will improve BEB benefits, of course, as we can take a guide from what we saw with the wind hydrogen, for example. But our analysis is based on today's reality and outlining that we will have to be looking at how the grid is developing in terms of emissions, so that Saskatoon Transit is ready to heavily invest in decarbonization alongside with that happening. Next slide. Another critique.
Sorry, Mohammed, we'll actually just stop there if we go back one slide. Also, just to flesh out, as Mohammed noted, because this is a really key point that folks had a lot of questions about, right, was the grid composition. So as Mohammed noted, we did use the figures actually provided by Saskatchewan's own grid system, its electricity operators. Having said that, we are cognizant that just recently in Saskatchewan, there was a decision potentially to extend the life of coal plants. And so we are aware that, in fact, a contra current to the nature of the criticism here, the grid that we modeled may actually be cleaner than the grid that Saskatchewan may actually experience with the extension of coal. Having said that, over time, of course, we're aware that the efficiencies of vehicles, and we will talk a little bit about also the fleet organization principles that may reduce the number of vehicles that draw on the grid and achieve the same success factors, that indeed that might help to reduce the emissions, even if the grid gets dirtier over time. So we will come to that at the end of the FAQ, just in terms of some of the general outcomes from this about what can happen in a city like Saskatoon to reduce emissions and reduce the replacement ratio and reduce the total vehicle kilometers consumed that drive up those emissions, even if the grid is not run by waterfalls. So we'll come to that in shortly, just after we go through the high-level FAQ. But I did want to flag that. Over to you, Mohammed. We can go through the next critique.
Thanks, Josipa. Another critique is that the report ignores the success of Saskatoon's BEB pilot. Now, this is incorrect. The report does not ignore the pilot. The pilot is rather a very important step throughout the decarbonization. But the report, the CUTRIC report, goes a step further by simulating performance across every single transit block in the system. A pilot is very different from a full rollout fleet. Our comprehensive analysis shows that to ensure 100% service reliability with current technology, solutions like en route charging are necessary, and block splitting as well, which is a complexity that you don't really face on a limited pilot. plus the high infrastructure cost, or investment comes into the full rollout rather than a pilot where you do have, you may have some power to use from your current infrastructure without doing major upgrades. Jessica, do you want to add something here?
No, I think what we're going to do is come back to that when we talk about the high level system overhauls that could happen to get to a cleaner, less costly deployment.
Of course. We also hear the critique that the report is short-sighted and focused only on high costs. As we've seen earlier, this is also incorrect. As we've shown, our final recommendation was based on 3 equally weighted criteria, as agreed with. The criteria was agreed with to be used with Saskatoon Transit, which is minimizing emissions, maximizing ease of transition, and maximizing cost effectiveness. The diesel base case ranked highest because it performed best across the entire balanced assessment, not only just on the cost. Social benefits were also considered as they are embedded within the objective of reducing life cycle emissions. Next slide, please. Now, finally, some critiques said key data in the report, like maintenance cost and GHG savings, contradict other studies. Now, this is partially correct, but it's important to understand why. Discrepancies arise because our figures are outputs of specific empirical modeling based on Saskatoon's data, and different studies use different assumptions. To account for this, we conducted several sensitivity analyses. For example, we found that even with much lower ZIP maintenance costs or higher diesel bus maintenance costs, the final rankings did not change significantly. And we're going to show this in the last
in the sensitivity.
We'll be showing later.
Perhaps, Mohammed, though, because this is a real point of concern, we'll spend a little bit more time here and give folks a little bit more context. So, you know, depending on where you are in the country, you may or may not be aware of all of the deployments. CUTRIC does do a national zero emissions bus database, and we're into our 6th national database. It is available to our members. So if you do represent a member organization like Saskatoon, you can get the full database. But we do have a couple older reports. I believe report number 4, it's every 6 months we do the database. I believe report number 4 is available to non-members. You can definitely get a hold of our CUTRIC staff, and we'll leave an email here if you want to take a look at it. But it walks you through every 6 months in Canada, which agencies actually have zero emissions buses, which ones have actually procured them, which ones are in the process of procuring them, and which ones are in the plan stage. We have roughly right now just under 5,000 promises for zero emissions buses in Canada. But as of today, we have about 355 zero emissions buses on the road, of which a handful are hydrogen fuel cell buses. So the bulk are battery electric buses. Many of the battery electric buses that are quote unquote on the road in Canada today, from TransLink through to Edmonton, through to Winnipeg, through to Brampton, York Region, in Quebec City and Montreal, Laval, in Kingston and Grand River Transit, you can count on 2 hands and a foot the agencies that have electric buses in Canada that add up to those 355. TTC and STM and TransLink are the big ones, and then there's a smattering around the rest of the country with Edmonton's larger deployment of Proterras. If you take a look at all of those 355 vehicles, and we monitor all of them at CUTRIC, a very large portion of them have faced significant, extremely high maintenance costs. And there's good reasons for that. We're only really into year 3 of buses being on the road in what we would call full fleet service in Canada. So that would be in TransLink's case, York Region, Brampton, TTC, and Montreal have had multiple years of the vehicles operating on multiple routes, on across multiple seasons for multiple years under the rugged conditions that they treat normal vehicles. And many of the other vehicles have not been on the road long enough. So we have empirical data coming in, but they may well have spent, very typical for us to see, 6 to 9 to 10 months, even up to a year, of the vehicles going through just problems charging, problems getting started, problems with cold weather starts. And then we have a whole host of early deployments, which we applaud because we're part of those early deployments. We encourage transit agencies to go get the technology, even if it's not perfect and we know it's going to fail because it's first, second, third generation, but get it because we all have to learn the life of hard knocks before we can buy 200 and hope that they work well. Some of those agencies, certainly out west, Edmonton is a great example, where the buses came, they should have been ready to roll. They should be operating perfectly, but they're not. They're often sitting on the depot floor or in the depot or out in the parking lot, not operating. And so when you look at their maintenance costs, the maintenance costs are really high because we calculate them off of vehicle kilometers traveled, right? It's a per kilometer cost. So lots of those electric buses, in the case of Vancouver, there's some. In the case of out east, there are definitely some. In Alberta, there are some that were early days, BYD buses, among others, and it hits all manufacturers. So I don't want to, target one manufacturer or another. We have about 4 manufactured type standard 40-foot electric buses, and then a handful of the smaller shuttles in Canada. And across all of those, there are buses that are sitting dormant in all the provinces that have electric buses, and they're not moving. And they're not moving because the parts aren't available, the knowledge isn't there, there's multiple issues with the vehicle, the engineering hasn't figured out the solution. There may be a solution eventually, but the vehicles aren't moving. And so that means that there's maintenance costs with no vehicle kilometers. So when Mohammed says we're pulling off of empirical data, and I know we were criticized for not using empirical data, the opposite is the truth. We have pulled from empirical data, but if you were aware of all the empirical data as we are, you would know that there are a lot of struggling zero emissions buses in Canada right now. And Canada's not alone. It's just that we're a little bit late to the game compared to Europeans who lived through these life of hard knocks 8 years ago and are out through third and fourth generation commercial deployments. So those costs can be extremely high. And although the promised land is that electric vehicles should be super cheap to maintain. And if you have an electric car like I do and have for 15 years, you know that is generally super cheap to maintain your electric car. But under the rugged conditions and the early generations of vehicles that have gone out the door in Canada, there are a lot of buses sitting dormant or not traveling the vehicle kilometers they should in the first couple years. And since we only really have 4 to 6 years of data, of which really only 3 are solid fleet deployment data, and even in those 3, we have failures of buses not operating at the level they need to operate, you can understand why, while it's controversial to use a higher number, it is in fact empirically sound. Having said that, in some agencies, some of our agencies have said, you know what, show us what happens if we ignore all the problems and we focus on just like how the buses should operate after we fix the problems. And Saskatoon's a great example. Early pilot of electric buses, had some problems to start with, got over those problems. They're operating pretty well now, the way that they should. So if we ignore the problem period and we cut out all the problems that people are really living through right now and still working with, and we just focus on the good performance, then we can drive down that cost. And we've seen the cost go down to 40 cents, 30 cents. And here Mohammed's done an analysis of 18 cents a kilometer. And that's the promised land. That's where we want to get to. We want to get to like the 10 cents to 20 cents a kilometer. We think the fleets can get there. They are not empirically there in Canada today. So when we run through the analysis and our team has gone ahead and said, what if, because that's a fair thing to look at, what if that analysis shows that we can get down to this promised land of 18 cents a kilometer? And what if diesel costs keep going up? Variability in international price points, supply chain constraints, war that causes price points to go up on diesel. And we have seen that, even recessionary conditions, followed by really hot periods in the 2000s. We saw the price of diesel go through the roof for a period of years. So those things can all happen. Combine those two things. It is true that we can reduce the price in Saskatoon's case by tens of millions of dollars. But it is also true that it doesn't reduce the price enough to come into parity with diesel. And so what will be needed there, and we'll talk about this shortly, is additional government investment. And in this study, we didn't assume that the Canada Public Transit Fund would fund 50% or 40% of the study. Many agencies ask us to not assume it because it's a competitive bid and you may not win the money. But if we did assume that, there would need to be about 100 million or so that the federal government puts into Saskatoon's decarbonization program for it to come in cheaper than the diesel, even when we use these aggressive best scenarios for BEVs and worst scenarios for diesel. So those are really important pieces to know. There are agencies that have gone ahead and have won a lot of federal money, funding and financing, and they are moving ahead. And with that money, it has dropped the price of their electrification to parity with diesel. And so that can happen, but a lot of things have to happen for that to be the case. So Mohammed, do you want to go through now the sensitivity analysis that we did on the back end? Because we heard loud and clear the criticisms and folks being concerned that this is the only driving factor. It is important. It's not the only driving factor, but it's also contextual. Over to you, Mohammed.
Of course. Thanks for the context, Josipa. Next slide. In the next slides, actually, next like 5-6 slides, you're going to see a table similar to this one. On the left of the table, and we are showing the original report result as they are. And on the right side, you'll see the sensitivity analysis results for an aspect that is being changed to showcase how things would change. And in this example, we're showing, we modeled the impact of zero-emission buses traveling fewer annual kilometers than what was assumed. This scenario, although it lowers the life cycle cost and emissions for zero-emission bus options, again, the only thing that changed is it improved the scenario 1 from rank 4 to rank 3, but the base case remains the top ranked option. Next slide, please. Here we're showing the sensitivity analysis. What if we apply an 18 cents per kilometer for a zero-emission bus maintenance cost? And the impact here will not be, of course, on the life cycle emissions. So we're just showing the total life cycle cost. The life cycle cost dropped by 80 million for the scenario 1. It's ranked now again 3rd instead of 4th, but still the base case is ranked 1st. So dropping the cost to this limit is still not enough to overweight the diesel. Next slide. Now, if we did something opposite, if we increased the diesel maintenance cost to around $1 per kilometer, what happens is, again, a similar story. So the total life cycle for the diesel base case increases. It increases a bit on the zero-emission cases because during the project cycle, we do have some contribution from diesel maintenance and diesel cost because during transition you would have diesel buses up and running up until the full decarbonization of the fleet. So with that, the ranking didn't change much. Next slide. As Josipa mentioned, what if we assumed a Canadian public transit fund of 50% applied on the zero-emission buses? How would the total life cycle cost look like? And in this case, scenario 1 was reduced significantly by around 180 million, yet still it didn't overweight the diesel in this case. And next slide. And that's mainly because of the life cycle emissions. Again, it's like the give and take. It's still 40 million more expensive than the diesel, but remember that it's 10-15% reduction in emissions. Now, in this slide, we're showing how clean does the grid need to be to have like a clear emissions advantage for the BEBs to overweight the diesel base case. We found that the grid's carbon intensity factor must drop approximately to 30 grams of CO2 equivalent per megawatt hour, which is nearly Ontario's grid. At that point, the BEB solution will improve from number 4 to number 1, as we see here, keeping the cost. Keeping the cost as is. So without even a 50% reduction in cost or 20% reduction in cost. You need the grid to be really clean as the Ontario grid in order to have this making sense. We know that Saskatchewan Power is working on a net zero 2050 goal. But we have to, as we said, we have to keep looking at the investment on that end in order for Saskatoon Transit to be in line with that, to get the full benefit for the community from the life cycle emission reduction. Beside seeing also looking at the cost effectiveness of the project as well. And next slide, it's the final one. Now here we asked how high the diesel maintenance cost should be for the base case to lose its top rank on cost effectiveness. The answer is extremely high. Our analysis shows that the maintenance cost for diesel bus would need to reach up to around $5.87 per kilometer. At that point, the total life cycle cost of the diesel would rise to 853 million, causing it to fall behind the BEB option or zero emission bus options in general, or specifically BEB option in this ranking. So this demonstrates the significant cost advantage of the conventional fleet under current and foreseeable market conditions. And back to you, Josipa.
Okay, thank you so much, Mohammed. Now, we don't have a ton of time, but we've got some really good questions online. So we're going to take a couple minutes here to address a few that we can at least get out the door, and then we're going to include all of the rest into an FAQ. We're going to answer one right off the bat, and I know a lot of folks put them in the chat rather than in the Q&A. But can you, Mohammed, for the first question, Jory Vermette did ask again about how is it that the base case fuel production of CO2 gets calculated, and why does it seem that it's lower in contrast to the BEBs? So can you go back to our slides here, Mohammed, if you can direct Anita, we'll just go back to the CO2 equivalent calculations. And let's go through again, not just the well-to-wheel components that are incorporated, but also the fact that we have to calculate the full fleet replacement ratio and the full vehicle kilometers traveled. And so from a fleet perspective, because of those additions, that's why the CO2 ends up being higher overall. So over to you, Mohammed, for that question. Oh, you're on mute, Mohammed.
Yeah, if we can go to the environmental life cycle assessment slide, we'll see that, yes, like the operational emissions of diesel are really quite high. They're not low. However, if we look at the scenario 1, the full BEV solution, you can see that the fuel production.
Just a moment, Mohammed, we'll just ask Anita to get to the slide here. So just to give her a second here, it's slide 14, Anita,
there
you can go back there. There we go. Yeah,
here it is. Yes.
There we go.
Yeah, so while the operational emissions of the diesel is quite high, and it's well known for us, the emission intensity factor for the diesel combustion, still for the BEB, for the fuel production, which is totally related on the grid intensity factor, is quite high. Plus, as Josipa mentioned, the replacement ratio for the buses takes part here, because the green part is showing the infrastructure heating and cooling, which usually uses natural gas to heat and cool your facility. And if you need more buses in the facility, you need more heating and cooling involved because you need more space, right? And that is going to add more extra green color if you compare it with the diesel base case. In case of Saskatoon, that the replacement ratio was not was 1.2 to 1, so it's decent. I wouldn't say the best replacement ratio we've seen. So improving the replacement ratio would reduce this difference again. Plus also the other contributions like bus manufacturing, or more specifically the battery manufacturing, in case of zero emission, that doesn't exist in diesel based case. I hope I answered this question.
Yeah, and I think there maybe one thing that we can point out there is just looking at that scenario 1, the full BEB solution, it does come in under the base case diesel vehicle, but then when you add it up, the core message there is when we add it up across all the vehicles, and then you have to have that 20% additional number of vehicles. And keep in mind, maybe just to add the reality of it, when you add more vehicles and you have to add those vehicles going out, they have to travel a deadheading distance. So they leave from the depot to the start of their block. That's now additional kilometers. every single new vehicle has to travel over a diesel. So folks might not realize, but in some cases, when we look at really hard routes, the deadheading is half the distance that the vehicle actually travels in the whole day. And deadheading is when you don't have any passengers on board. You're just getting to your first start. And the more we have vehicles replacing diesels at a higher replacement ratio, the more deadheading there is. So those kilometers add up, they eat up energy, they start to add to the fleet-wide emissions. And in some cases, you see the fleet-wide emissions for the battery electric buses, because you're adding more vehicles, more kilometers, is greater than the diesel, even though bus to bus, the electric is lower than the diesel. That's pretty common in Canada. And I know we've hit 2 o'clock, but Mike, with your approval, if we're okay to go 5 minutes over, we can try to tackle a couple more questions. We know we're going to lose a few folks, but there are some really good questions here that we did want to tackle just to go through. So one, if we can go to the implementation slide, and Mohammed, if you can just direct Anita on the slide number. The question from Peter Galen is, it looks like our report only looks at all electric or all hydrogen, but we didn't look really at what about the going from diesel fleet to a mixed diesel and electric fleet to a fully GHG fleet. So perhaps to clarify, and we'll just move through to the implementation plan slide here. In fact, Peter, we do exactly what you say. So we never assume that the transit agency from 2025 to 2026 is going to buy 200 electric buses and go all electric. Our implementation plan is year by year. And there we go. Yeah, there we go. If you want to go back there. Yep, we'll just pause there for a moment. Thank you so much, Anita. If you take a look at the implementation plan, we'll just spend an extra minute here. We take a look at here, if the start year is 2027, then by 2030, how many BEVs do you have to buy, or fuel cell buses, depending on the scenario, or the mixed green fleet? So I'll just look at the top scenario here. The implementation plan is stage 1, there would be 66 battery electric buses bought by 2030, but the diesel buses are still operating. So in the full report, we have another chart that shows you're growing the 66 BEVs, but the residual, the other 140 plus vehicles in Saskatoon are still the diesel hybrids. And then you go into 2031, from 2031 over to 2035, another 157 BEVs are brought on as the diesels retire, but there's still diesels in the fleet. And so it's not an instantaneous switchover. It's from 2027 to 2041. There is a certain number of BEVs being added every year, but the diesels are still there. They're still operating. So hopefully, Peter, that answers your question. Every scenario assumes a gradual implementation of vehicles, and we're replacing vehicles as they retire. Most transit agencies in Canada, not all, but most, do not advise us to assume that they will retire vehicles before the natural life cycle of the vehicle. So vehicles in Canada will typically last anywhere from 12 to 18 years. Some transit agencies hold on to them for 22 years, where the maintenance cost really goes up. And they do that because they don't have enough money to buy brand new vehicles. So nobody wants to see a new diesel bus retired after 2 years, because that's an epic waste of emissions from the manufacturing and a huge waste of capital money that nobody has from tax dollars. So here, the implementation plan here, like everywhere else, is based on the natural retirement schedule of the vehicles already in the fleet. So rather than replacing a retired diesel bus with a diesel bus, you could see from 2027 to 2030, there is a natural inherent replacement of 66 vehicles. Now, the reason the number is different between scenario 1 and 2 and 3 is because the replacement ratio. So when we're calculating out here in scenario 1, we're looking at you only need 66 BEVs if you're using en route chargers to replace an equivalent amount of vehicles in diesel, or the service that those diesel vehicles that are retiring would have served. In other cases, you may need more in the case of fuel cell buses, because it's running out of hydrogen on the really, really hard segments that we're looking to shift over. So that is part of the implementation planning. And it's not just the retirement schedule that goes into it. It's also how fast can you integrate chargers. So you may need more than 66 battery electric buses in those first few years, but integrating chargers and creating the depot space is another factor that goes into considering how fast you can integrate these vehicles. And in some cases, the transformer can't handle it. So in some cases, the implementation is delayed by how fast the utility can upgrade the transformer that feeds into the facility. So all of those factors go in. I hope, Peter, that answers your question there. Mohammed, is there anything else you want to add there about the implementation plan and the fact that it is assumed that it's a mixed diesel electric or mixed diesel hydrogen fleet for the bulk of the years until 2041?
No, actually, you captured that very well, Josipa. It's as we were talking earlier, like even if we look at the timeline here that was proposed in the study, based on the replacement timelines that Saskatoon Transit, knowing what we know right now, it looks like okay, we may have to slow down the purchases. Instead of 66, for example, we can do 20. I'm just throwing a number here, just to balance our knowledge now that the grid has to be cleaner before going with heavy investments. That's the message here. So yes, it is already a mixed fleet because you have already a pilot that was up and running and successful. And so it's up to the change management here in Saskatoon Transit to see how they wanna increase their fleet, zero-emission fleet, with the demand of knowing much more about their routes, performing on zero emission, but not knowing that this is not gonna give the benefit for the community, back to the community in terms of emissions. So having this in mind would help in planning properly how this mix would look like in the near future and in the far future.
And perhaps what we can do is conclude on some high-level items, and then I do just want to answer a couple questions Kaylin Lee had there as well, and Kurt, and then we will try to capture the rest we will definitely capture the rest in the FAQ. But to the point that Mohammed was referring to, and just at a global level, if we were to start with, okay, it's not a perfectly beautiful grid right now in Saskatchewan or in Alberta or in a couple of the maritime provinces or in the Northwest Territories and in some of the territories, it's not a perfect waterfall grid. And if you're okay with nuclear, it's not a nuclear grid either. Okay, we get that. So what would we need to do in these locations? Because we've gone through the same thing in Alberta. We've modeled a whole bunch of agencies in Alberta, especially small agencies, where they're also in a grid that is decarbonizing, but it's not pure waterfalls right now. It's definitely not nuclear. So if you don't have that, what can we do? Well, what we can definitely do with transit agencies, and some have asked us to do this already, is reduce as much as possible the replacement ratio. That's number one, is if every bus could replace a diesel bus 1-to-1, which today cannot happen. And I hate to burst bubbles, but it's probably never going to happen, because as much as there's the promised land of new battery capacities, in automotive, where there's tens of millions of units sold every year, battery manufacturers like Samsung and so on are innovating rapidly for car sales, where you can charge people a lot of money to buy an electric car. That is the nature of the industry. And so a lot more effort is going into longer range batteries for cars. But in the bus world, the volume is very, very small. And those car battery manufacturers will not sell to bus manufacturers. It's not happening, and it's likely not going to happen. And we've been on the front lines of those negotiations. And it's because the volume is very, very small. So the price is very, very high. And just to give you an example, it is very typical for bus manufacturers to be paying well northward of $500 a kilowatt hour, up to $1,000 a kilowatt hour. In the car world, you're looking at $100 a kilowatt hour. Okay, so the differentials are huge. And as a result, the innovation going into the batteries for the price point that transit is able to afford is starting to plateau. And so we've hit about 550 kilowatt hours as a battery pack, and that's considered massive and big. In Europe, they're way smaller because there's a lot more frequent stopping, a lot more frequent charging, smaller battery packs, etc., less rugged routes. So we're kind of hitting the plateau of innovation in North America. If anything, there's a pressure to go the other way because these things are so expensive. You're driving around with a really heavy battery pack that you have to replace at 7 to 12 years at hundreds of thousands of dollars. So the innovation on the battery pack is not going to save the day. What's going to save the day is by operational changes. But operational changes can be hard. So in some transit agencies, they've said to us, okay, imagine that no bus returns to the depot in the middle of the day. So when it runs out of power, it's charging up en route. Mind you, these en route chargers are $1 million a pop. They are not cheap, right? They're not low cost charging systems at the depot. They're over $1 million plus civil works, easily $1.2, $1.3 million to install. So they've got en route charging. But then imagine on top of it that your drivers hand off in the middle of the road. Some transit agencies do that. So drivers will drive up and they'll hand off at a transit stop. So the bus is not going back to the depot and coming back to the starting point. If you do that, we can cut a lot of vehicle kilometers. And if we then really look at every route that Saskatoon delivers and run AI and some optimization through the routes, we can really get to optimize blocks to minimize deadheading. And then you can tell your drivers, you have to turn left here, turn right here, turn left here, turn right here to go from depot to starting point. Most transit agencies don't tell their drivers how to get from the depot to the starting point because it's a labor issue, it's a union issue, and it's a rights issue. If we were to use those operational mechanisms, we could radically reduce vehicle kilometers and reduce vehicle replacement ratios. Those are just some of the things that could be done. But there are operational costs to that on labor, contracting, and other issues that have to occur. So those can be done. That would reduce the emissions, and it would reduce vehicle kilometers, and it would reduce cost in even a grid that is like Saskatoon's. And then, of course, we can lobby for the extension of the Canada Public Transit Fund, which we have done, which is the single largest investment by the federal government ever in the history of Canada and has motivated large sustainable volume purchases. The more that that program continues, the more that those 355 buses in Canada grow to 5,000, volume pricing of manufacturing will help to drop the price point. Mind you, to burst a bubble, price points have jumped up recently because of tariffs. But assuming the tariff war ends, assuming we come back to stability, and assuming volume goes up, price points should come down naturally, even if battery pack points don't come down in and of themselves. And hydrogen should come down as volume goes up. So these are all some things that can happen. There are many more things that can happen to optimize the way that a transit agency works. The summary is that most transit agencies historically have said to us the technology has to work like diesel. And now most agencies, including our colleagues at Saskatoon, who are very well aware of this, are aware that it's never going to work like diesel. So the system has to come halfway. The system is going to have to change the way it operates halfway, and the transit technology has to come halfway. And that's where we're going to be able to reduce vehicle kilometers, improve emissions, reduce costs, and get to a decarbonized fleet faster and sooner. But that speaks to hopefully, Kaylin, your question about how have we validated these results. I'll answer that one. We currently have another 3 projects. One of them is with the Association of Electrical Industries in Quebec, the AIEQ, and that is a project that is soon to be announced. And we are monitoring the electric buses in real time of 9 transit agencies. We have just completed our first internal report to the 3 transit agencies that provided their data into that first report from the last few years. We have been monitoring those electric buses through our Pan-Canadian Electric Bus Demonstration Project with Vancouver's TransLink, York Region Transit, and Brampton. Those were a total of 18 electric buses and 7 overhead chargers over multiple years, where we tracked in real time from the telemetry devices the performance of those vehicles and their charging systems. We've expanded that to capture the bus performance up to 2024. And we've now brought in a series of other agencies, an additional 6 agencies who have buses on the ground, and we're tapping into all of their bus performance. So that project is starting to, well, it has already produced the results, and we have been able to validate for the last 3 years that our predictions are very much in line with performance. So we're very safe and secure that our algorithmic tool sets have been validated and balanced by empirical reality. We have another project called the Opta Dashboard that the Ontario government has supported that is growing into our national ACES data trust. And this is a project where we are starting to incorporate, again, about a dozen transit agencies that have electric buses on the road, many of them the same ones in our AIQ project, in a real-time dashboard where the agencies themselves can see how their buses perform and chargers perform compared to other agencies that may have the same buses and chargers and fueling systems. That is happening, and we're working with the federal government to create a funding pool to digitize it and cyber securitize it. And our goal is every electric bus and fuel cell bus in the country will be monitored through a telemetry and tracking device. And therefore, we will be able to give the power to the cities to look at real-time performance compared to promises and performance of different makes and models over time in real time. So that is happening. The third project that I mentioned has already come and gone, and we were able to do our first validations off it, and that was our Pan-Canadian Electric Bus Project, which you can read about on our website. So we've got a lot of validation happening. We're very secure in our numbers because we're the only organization that has access to that many electric buses, well, the full panoply of vehicles in Canada, and we are part of the European Jive network and their electric bus joint procurement network. So we have been monitoring European vehicles as they've been sharing data with us as well. And the last but not least question is Kurt McCosen, you've asked as well, to that period, if the pilot projects are so different than a full rollout, why don't we just ignore the pilots, or should we ignore the pilots, and what's the point of a pilot? And perhaps I can pass to Mike. I mean, I can speak from real-time experience. We led pilots because we knew stuff would go wrong. And the reason we do pilots is because there's a lot of sales out there, and we believe in science over sales. And 8 years ago, there was lots of sales promises, including from bus manufacturers that are now bankrupt. And so I don't feel bad about talking about Proterra and Lion Electric Bus. They're not the only ones, though. Lots of sales promises about the performance, 1 kilowatt hour per kilometer, one-to-one replacement with diesel. They can work in these ways. And we knew that if you applied them to real world conditions in transit operations, that it probably was not the case. That was probably sales and not science. So the pilots really proved that out, and they helped to modify the sales promises with the reality. And from that, you also get the time at the transit agency to train your staff. Because it's not like today a mechanic comes in and tomorrow she's an electrician. That just doesn't happen. You have to learn over time, and you have to recruit some staff, and people have to be retrained, especially with trades and tickets, on how to manage some of the stuff. Your emergency personnel need to be updated. Your EMS system, your firefighters need to be updated. A whole bunch of things have to happen. So pilots give the time and space to do that before you go all in, gangbusters, and buy a bunch of vehicles that then your whole system, your workforce is shocked about. And Mike, you may have some insights there too, because you guys have lived through it.
Yeah, I would say the difference between a pilot and a study helps understand what the opportunity looks like, and a pilot really helps solidify what those issues and the things that you don't know are on a smaller scale, because as Josip is alluding to, once you're knee deep into something, it gets to be much more difficult to pivot and put yourself in a place of success when you're just keep moving forward on something without fully understanding the impact. And when we're talking about something like the reliability of a transit fleet, it's really important for us to fully understand and fully comprehend the impacts of our decisions and how operationally the changes become. Because at the end of the day, we're debating technology and the way that something that, the technology of how the vehicle moves. But what we're really talking about is making sure we can reliably move the citizens of Saskatoon and do so that way they can get where they're going on a daily basis. It's not like these pilots are test fleets moving people, not moving people around. So it's really important that we're always understanding and considering those variables.
That's great, Mike. And I know we've taken folks over time, so we'll conclude on two last ones. One is, Kaylin, you had asked, do we take into account the global triple bottom line elements and the other aspects of climate change as a benefit? And as I noted here, specific things like what is the cost of pollution on healthcare and cardiac arrest, and how many infertility cases are there because of pollution? No, those are not part of the scope here. But we recognize that those are the costs of climate change. There are certainly other costs of climate change, like geopolitical intolerance and geopolitical damage and wars. There's famine, there's agricultural dehydration, of course, and devastation. So there's lots of inherent outcomes to climate change that we all respect. In this study and the Zero Emissions Transit Fund, those internalized costs of those elements of global climate change or regional climate change are not part of the scope. Potentially they can and should be, and we've certainly advocated for that. But the most important thing to walk away from is these studies, the Zero Emissions Transit Fund, CUTRIC helped to create that fund, and we advocated for that fund. It did not exist federally years ago. We advocated for it on the premise that climate change itself is not good, that human-centered climate change and human-caused climate change is inherently a bad thing for most communities. While we may mitigate and while we may adapt, in general, we need to attempt to mitigate as much as possible. So the underlying component of your question, Kaylin, is the reason this study is being done, and the reason all of these studies are being done and funded, and the reason the policy was created and CUTRIC led the development of the policy at the federal level, is because we all agree that there are inherent benefits to avoiding climate change and a lot of damage to allowing climate change to unfold. Now, in the weeds, our job is to address very technically, how can decarbonization happen with the resources we have? Because money doesn't grow on trees. I wish it did, but it doesn't. There's only so many dollars a transit agency has. with the energy grid that the agency has access to in the foreseeable future and today, with the limited number of products available in the marketplace. Because we may wish that the manufacturers produce super vehicles, but they're not. They're just not. And so they also don't appear magically. So when we take those three things into account, what we're doing here is the technical guidance on what can you do with the resources you have, the money you have, the grid that you have, and the vehicle products that are available, recognizing that we all assume a priori climate change is not a good thing. That is inherently not good. So hopefully that answers your question there. We will pause because we've taken everybody 20 minutes over. We truly apologize for that, but we really did want to make sure that we tried to address as much of the concerns as possible. We did have an ask about how much of this will we share. We're going to get our approvals from Saskatoon Transit and from all the input providers. And we would like to be able to share this presentation on our landing page on our website. We have several dissemination websites. So if you want to look at the results from the Brampton Transit work, several others that are on our website, and our dissemination pages have just started to be developed this year as most of the studies concluded this year. And we are starting to put the public relations piece up there, the science communication for educators and for members of the community. So stay tuned there. We will take all the other questions we did not get to, and we're going to flesh them out in an FAQ and post on our website as well. I want to thank you, Mike, for your time. Thank you, Bernard, Mohammed, and to the CUTRIC team for putting this together. And thank you also to the Saskatoon Council for working with us to make sure that public dissemination is a core part of this, since it's a core part of our vision and mandate as well. Thank you, everyone, and have a wonderful day. Thanks so much, Mike. We can let you go now, and we're just going to hold the line here so we can make sure to copy all the Q&A and chats, and we'll follow up with you. Thanks very much.
Thanks. Sounds good. Thank you, everybody.
Take care.